Hey everybody, welcome back to chemistry. And so now what I want to do is talk about a physical process called dissociation. And so this is often used to describe how ionic compounds are able to dissolve in water. So if I can increase the slide. So dissociation is a description of how an ionic salt can dissolve in water. Here we are assuming that the salt is completely soluble in water. And a good example of this is table salt dissolving in water. So what happens here is that we have solid table salt up here, which is, of course, the ionic compound sodium chloride, and it drops into the water. And what it'll do is it will separate here into ions into the water. This process of the solid salt separating into ions in the water is called dissociation. So what I want to talk about now is a little bit in more detail what dissociation is. And so let's say you have an ionic salt, and it could be, as an example, sodium chloride. That is an ionic salt, or any other kind of ionic salt, like aluminum fluoride. When you dissolve these salts in water, what is going on is that you are creating solutions of ions. And so this process of taking these ionic compounds and creating solutions of ions is called dissociation. So to understand that a little bit better, I think it's really good to understand sort of what's going on at the molecular level so that we can write chemical equations that represent this process of dissociation. So let's start out with a simple example here. So let's say you have sodium chloride salt at the end of the spoon there, or let's say you're just dropping in the water. And let's say you just add enough so it all dissolves in water. So what you probably will see as it's dissolving is that the crystals basically disappear. And so that reflects what's going on at the molecular level, is that you have individual ions in these crystals being yanked off by water molecules, and they're being separated out. And that process is called dissociation. So let me sort of highlight what's going on in this picture. So here, maybe on the left side, what we have here is this crystal here of sodium chloride. Now, if you look at the lower portion, we see something kind of interesting going on. You can sort of see here in the lower portion, we have three water molecules ganging up pretty much on the poor defenseless negative chloride ion. So green is the negative chloride ion. And so you can see the waters are ganging up with it, and then they're forming bonds, weak bonds with the ion, so they can pull that negative ion off. So one little detail to sort of notice in this picture is that we have the hydrogens that are pointing closer to the negative ion than the oxygen. The hydrogens are in white, the oxygen is in red. And there's a specific reason for this. The hydrogens sort of have a slight deficiency of charge, and so they're a little bit positively charged. And on the other hand, the oxygen has a slight excess of charge. So it has a bit of a negative charge. And so the water molecules are going to orient their positively charged hydrogens toward the negatively charged chloride ion. And then that will be able to pull off the ion. And then when the ion is pulled off, this is what happens. What you can see is the ion here, the chloride ion, the negative ion is pulled off. And what you'll notice is that now it's surrounded by several water molecules. And again, because the hydrogens have a slight deficiency of charge, they're slightly positive, the hydrogen ends are going to be pointing toward the negatively charged chloride ion, while the oxygens of the waters will be kind of pointing away. Now the opposite thing happens with sodium. Now water molecules will gang up on a positive sodium ion, but they're going to point their oxygens toward the sodium. And the reason is because the oxygens have a slight negative charge. And so they'll be drawn to the positive charge of the sodium. And so when you have several water molecules yanking off the sodium will be pulled off the crystal, and then the sodium ion is now surrounded by water molecules, kind of like the chloride ion, but in the case of sodium, the oxygen ends of the water molecules here are kind of pointing very close to the positive charge of sodium. So this will happen over and over and over to all those ions into the crystal until all of the positive and negative ions that are jumbled up in the crystal have been pulled off, and they're all surrounded by water molecules. When that happens, then it's said that the sodium chloride is fully dissolved. And so this process is called dissociation. And so I've got some notes on it here. And one thing to note is when the ions are completely off into solution or surrounded by water, you would say they're dissociated ions. Now, you will note below how I've represented this process by an equation. And so that is an equation for the dissociation of sodium chloride solid in aqueous solution into dissociated sodium and chloride ions. And so what I want to do next is get some practice writing equations for ionic salts being dissociated in aqueous solution to ions. So we'll do that next. So we'll go to the board here. So let's go over that a little bit. So let's say you have calcium fluoride. And let's say you dissolve this in water. So first off, the calcium fluoride is a solid salt, and so we can indicate that with a state symbol by putting an S here. Now, you're going to dissolve it in water. Can you write a correct chemical equation to describe the separation of the calcium and the fluoride ions in water? So this would be an equation for the dissociation of calcium fluoride into calcium fluoride ions. So the first thing I want to do is I'm going to make a slight mistake to make a point, but then I'll do it correctly. So some people make this mistake and try not to do this. But here, calcium is fine so far. Now, what a lot of people do is they'll say, oh, okay, so it's F2. So they will write F2. Okay, that is not correct. And so let me explain what the correct answer is. Okay, so what you have to sort of imagine what is going on in this compound is why is it that two fluoride ions are part of a formula unit that includes one ion of calcium? And so one of the things you'll have to remember is that calcium has a 2+ charge. So when the calcium ions are yanked off by the waters and are separated off, now you have calciums that have ion. You can see that we want to represent those ions with a 2+ charge. So we indicate the charge in the elemental symbol. And then we indicate that the calcium is now surrounded by waters by writing a state symbol for the calcium ions, which is AQ. Now, going back to the formula unit, you might remember when we're taking a name of a compound, we're writing a formula, we need to balance charges. And so we took two fluoride ions, each with a negative charge, to balance a single calcium ion with a 2+ charge. And so here what we have to write in the dissociation is the fact that each formula unit is really you have two fluoride ions stuck to the calcium, but then when it drops into the water, the calcium separates and the two fluoride ions separate from themselves, each with a single negative charge. And so we have to indicate that. So to do that, what we do is we indicate we have fluoride ions, each has a negative charge, and we have to balance this and show that the two fluoride ions separate from each of these calciums. So we put a 2 here, and then we write an AQ here to indicate that these ions are dissociated into the water. Okay, so there's that one. Let's move on to the next one. Okay, how about barium hydroxide? Okay, so if you had barium hydroxide salt and you were to dissolve that in the water, can you write a chemical equation that describes its dissociation? So let's go ahead and do that. So you have barium hydroxide, and so we have to include a state symbol in the dissociation equation. If it is a salt, it is a solid, so we will put a parentheses S here. And then when we add this salt to water, you get the barium ion dissociating from the two hydroxide ions. So you have to remind yourself the reason why two hydroxides bind to barium, each hydroxide with a single negative charge, is because a single barium ion has a 2+ charge. We have to indicate that in the dissociation equation. So we write Ba2 plus, and to show that it's dissolved in water, we write aqueous. Okay, and then here the hydroxide ions, each with a negative charge, separate from the barium. So we have two hydroxides that go off from the barium. So we write 2OH like this, and then aqueous. And so that should be a good equation to describe the dissociation of barium hydroxide into barium and hydroxide ions. Let's do the next one. Okay, so the next compound is copper nitrate. Okay, so copper nitrate is a solid, which you can add to water, and then what will happen is two nitrate ions will separate from the copper ions. So are you able to write this? So what I would write is Cu, and it looks like the charge of copper. Let's figure it out. We have, you may recall that copper can either be a +1 charge or a +2 charge. So we have to sort of figure that out. We have to indicate the correct charge here. So each nitrate has a single negative charge. We have two nitrates, so we have a total of -2 charge here. We have one copper ion in this formula. So to balance the -2 charges contributed by nitrate, copper must be +2. So it's copper 2 plus. And again, when it dissociates, it'll be surrounded by water. And so we indicate that with a symbol of AQ. And then we write out two nitrate ions like this. And that should be a good equation for the dissociation of copper nitrate in water into copper and nitrate ions. Now, importantly, with the dissociation equations, what I did is I chose compounds, calcium fluoride, barium hydroxide, and copper nitrate that all dissolve well in water. If you can get a lot of mass of these compounds dissolved in water, it is said to be a very soluble compound. So that's important to note. So we will now move on.